Hey guys, I'm Tony Lyons. Welcome back to the CG Compositing series. Today I'm going to talk about another chapter in the Material AOVs section, and I'm going to cover some light science and cross polarization. While doing my research, I found that this is a pretty interesting field that I didn't quite know too much about before I went into it, and I think it helps separate the idea of diffuse and spec on a very scientific level in the real world and what goes behind cross-polarization photography. So let's just start jumping into it. Okay, so today we're going to be talking about some cross-polarization photography. And that is a specific type of photography that allows us to actually separate the diffuse and specular components in real life from a photograph. And as you can see, there is a picture of a boot or a shoe on the left side, and we have split out diffuse and specular components of that original image. This can be really useful for recreating the shoe in 3D and using these photographs as textures and photogrammetry. So let's get scientific and nerdy about light. Visible light is a section of the electromagnetic spectrum. Light in color is represented in 2D as a sine wave with a specific frequency. So lower frequencies are more in the red range, and then they turn more green, and then higher frequencies get to blue and violet. This is the section of the electromagnetic spectrum that we can see called visible light, and you can see when things are higher frequency than we can see, they become ultraviolet, and when they're lower frequencies that we can see, they become infrared. We've heard of ultraviolet and infrared before. Those are areas of the electromagnetic spectrum that we cannot see, but for example, cameras can pick them up, and we kind of generally know about them. 3D light wave representation. So in 2D, the representation looks like a sine wave, but the 2D representation looks a bit different in 3D space, since the light waves could be oriented in any random direction, any and all direction on its forward axis. So it kind of makes this this sort of shape here in three-dimensional space. You can imagine that it could be anywhere along that 360-degree angle. But we're just going to represent it here as sort of this kind of cross section. So we're seeing the different orientation that is possible along its forward axis there. A light beam with randomly oriented light waves, like this picture here, is referred to as unpolarized light. And this is how it is sort of represented either in a straight-on view or in a three-dimensional view, or sort of like with these cards here on this picture. Linear polarization of light. This is referring to polarized films that you're putting in front of a camera. So linear polarization isolates one specific angle of the light wavelength, only allowing a sliver or a portion of the light waves that were oriented in that direction through the filter. Here you can see there is a vertical polarizing filter, and this is our unpolarized light. You can see the different angles that it could be oriented in. And when it passes through, all those other angles are blocked out, and only that vertical angle, or whatever angle that this polarizer is oriented in, that is the only angle that is going to be allowed through. So here's another image where the light is coming in this direction, and some different orientation of these kind of cards that are representing unpolarized light. This polarizer is facing a specific direction and only allowing that direction of light to go through. So only half the light is allowed to pass through that filter. Here we have two animated examples that might help illustrate the point a little bit more. On this left example, we have some unpolarized light coming in that is represented by these different angles that are shaded in different colors, and it is crossing through a vertical polarizer, and only the vertically angled light rays are going to be allowed through. And on this side, it is a horizontally angled polarizer, and only the horizontal rays are going to be let through on the other side. On the right side, we have a 3D representation of the linear polarizer, and the color that you see here is just representing whether or not it is a vertical or a horizontally angled light ray. So we have unpolarized light coming in, and it's hitting this polarizer, and depending on the angle of the polarizer, it is only letting in a section of the light ray. Cross polarization of light. So we just talked about what happens when you put a linear polarizing filter in front of the light, But what happens if you put two linear polarizers in front of each other? So then you get cross polarization. Cross polarization uses two polarizers that are perpendicular to each other, effectively eliminating the light wave passing through. So the first polarizer isolates the light wave to only one orientation. So in this case, only a vertical light is being let through the first polarizer. The second polarizer, if parallel to the first, continues to allow the polarized light to go through it. So if this second polarizer was also vertical, the light would continue to pass through because it is oriented vertically, and it'll just continue to go through that polarizer. But as you turn the second polarizer so that it becomes more perpendicular, the light gets dimmer and eventually gets blocked entirely. So that is what is going on in this graphics here. So you can see they're here both aligned, and then as you turn the second polarizer to become perpendicular, what is happening is that this light is shrinking, so it's dimming in a way, and then it is finally ceasing to exist, so it's getting blocked entirely when it becomes fully perpendicular. So here we have an example of somebody turning some polarizing filters, and as they do so, if they're parallel, the light gets let through like this, and as they turn it to become perpendicular, all the light is blocked, and it gets dimmed as they turn it. So we might want to look at this 3D representation to get a better understanding. So we have the unpolarized light wave. It passes through the first polarizer and is vertical in this case. And if the second polarizer is the same orientation, so vertical, the light will continue to pass through. And as the polarizer turns and becomes perpendicular, the light dims and eventually gets blocked entirely, so no light is let through. Polarization upon reflection. When unpolarized light hits a reflective surface, and that reflective surface has a refractive index that is different than the surrounding medium, such as glass or snow or water, the specular reflection is polarized or partially polarized to the angle perpendicular to the plane of incidence along the surface. Now, that is a mouthful. We can see a representation on this left side. We have unpolarized light coming through, and let's just say that this is water. So what this refractive index is talking about is that some of the light is passing through. So that's why it's like glass or water. Like some of the light is able to enter the surface or get refracted into it, and some of it gets reflected. And in these particular situations, along the surface, so in this case, you see some plane, maybe some water here. The unpolarized light along the surface is the direction of the polarization. So in this case, it is going to be horizontally polarized. But you could imagine that if we were looking at glass that was a storefront or something, then it would be, I don't know, vertically polarized. So it's just polarized flush with that surface direction. So the reflected light might only be partially polarized and not fully polarized, and how polarized that reflection is depends on many factors such as angle of incidence, material type, etc. Brewster's angle. So at a specific angle, the specular reflection is completely polarized to the angle perpendicular to the plane of incidence. So I tried to represent this in 3D that depending on the angle that this unpolarized light is hitting this reflective and refractive surface, the outgoing light is either remaining a little bit of the polarization, and then at a specific angle, the unpolarized light disappears and it is completely polarized. And that is Brewster's angle. The unpolarized diffuse component. Only the specular reflection has this effect of the Brewster's angle polarization. The diffuse component is unpolarized because they are newly emitted photons from excited atoms of the material. We sort of learned this in the previous video where we talked about diffuse component being light hitting the material and interacting with the molecules. And the molecules get excited and they themselves release the new photons into the environment, which is what we are perceiving as the diffuse color. So because they are newly emitted photons from these excited atoms, they are then unpolarized because they could be oriented in any direction. This phenomenon only happens when light is reflected off of dielectric materials such as water or glass and not metals. When reflection occurs on a metallic surface, no Brewster angle nor refracted light exists. So just a reminder in this little video here, light photons hit and excite atoms which emit new photons and excite nearby atoms. Since it's a newly created light wave, it could be randomly oriented in any direction, meaning it is unpolarized. Here is a little 2D graphic here where you have linear polarized light that is hitting the surface, and the incidence light is also linear polarized, so the specular reflection is the same polarization as the incoming light, but the diffuse reflection is unpolarized. See this representation here where I'm sort of just shooting these unpolarized diffuse rays that are really tiny in all directions, and then you can see this Brewster angle specular reflection that is polarized. Okay, Tony, why are we talking about all this stuff? So we have polarized specular reflections. Placing a linear polarizer filter in front of the observer will cross-polarize some specular reflections if angled correctly. It blocks the polarized reflection light wave from shining through it. This is how polarized sunglasses are able to eliminate harsh glares and reflections from dielectric surfaces such as glass, water, or snow. So in this image we have a harsh specular highlight on the water from the sun, and it is being Brewster angled and polarized, and you can imagine that it's horizontally polarized as it's hitting this camera or this guy's eyes. And when he puts on the polarized sunglasses, the polarization of the sunglasses are vertical, and so that blocks out the specular reflection, and all that is left is the specular reflections that are not quite fully polarized, so at a different angle or so, and also the diffuse reflection of the environment. So you can go from seeing a harsh specular reflection from the sun to inside of this puddle. In this example, we have a man holding a linear polarized filter, and in the beginning, the specular reflection is being allowed through because they're both polarized in the same direction, so the light is able to go through. So if the specular reflection was horizontal, then the way that he's holding the filter is also horizontal, and that light is allowed to go through. And as he turns it, the specular reflection seems to kind of like fade off, and that's because it's slowly dimming and then getting blocked completely by cross polarization. He is able to then eliminate the specular reflection and see into the water. This is also why fishermen tend to really like polarized sunglasses, because it's eliminating the glare of the sun on the surface of the water and allowing them to see the fish under the water. Here's a few more real-world examples of somebody with a linear polarizer on the lens of the camera, and they start allowing the specular reflections to go through, and then they turn the filter so that it is then blocking any of the specular reflection from being able to reach us. And the image on the right is sort of before and afters with polarizers, which is, blocking out the reflections of specific types of surfaces like this glass or this road that has a very strong glare, or the snow that is reflecting the sun at a specific angle and then getting blocked by the polarizer. This is my 3D representation of the polarized specular reflections. So you have unpolarized light that is coming in and hitting this reflective surface, and then the reflection is being partially polarized or completely polarized depending on the angle. And then we have a linear polarization filter in front of the camera, which is either allowing the specular to go through if it's the same angle, or if it's perpendicular, so in this case if it's vertical, it is then blocking the specular. However, because the diffuse of the surface is unpolarized, it will still show the diffuse. Cross-polarized photography. So we just talked about how unpolarized light hitting certain surfaces gets polarized, and then with sunglasses could block the specular. So what happens if you polarize the light source? If you polarize the light source, the specular reflection is also polarized because it is a mirror reflection of the light wave. So this is going to polarize the specular reflection on all surfaces, not just water and glass and specific, refractive index surfaces at specific Brewster angles. It's going to be anytime you see a specular reflection from that polarized light source, it is also going to be polarized. Now the diffuse component is still on polarized light because it's the newly created light waves, photons shooting out from the material, that are oriented randomly. So adding a second polarizer on the camera means we can block the specular component entirely depending on the angle of the polarizers. When the two polarizers are parallel, we'll see the specular and the diffuse component, and when they are perpendicular, we will only see the diffuse component because the specular will be blocked out. Let's walk through it in this example here. We have our light source, and the light coming from the light is unpolarized until it hits the first polarizer. So this could be a film that is just sitting on the light. And now we have, in this case, vertically polarized light that is passing through. It hits a material, and that material has a specular component, a specular reflection, and that specular reflection is also going to be vertically polarized. We have also the diffuse component. These are new photons of light, and they are going to be unpolarized, so they could be oriented in any direction. Now, this is very convenient for us because on one hand we have a polarized component, which is the specular reflection, and on the other hand we have this unpolarized diffuse component. That is represented here in this little graphic, where the red line is the vertical specular reflection, and then the omnidirectional blue arrows are the unpolarized diffuse reflection. Now this passes through a second filter, and in this case, these two filters are perpendicular. So that means it's going to block the specular reflection, because the specular reflection is only existing in the vertical axis, and then it gets blocked by this horizontal filter. And what also gets blocked is half of the diffuse component, because it is a filter that's only letting in a certain angle. So because the specular reflection is now gone, we are left with only a partially polarized diffuse reflection. We can walk through it again in this example. We have a light source that is hitting the first polarizer and getting vertically polarized. That is hitting the surface, and it's broken into specular reflection, which is going to be the still polarized, in this case vertical polarized light, and then a diffuse component, which is going to be unpolarized. Now these two components hit this second polarizer, and when it hits that second polarizer, the specular component gets blocked out completely, and it only lets this partially unpolarized diffuse hit the camera, which is why we see the specular as being gone and only see the diffuse. I tried to represent this again in 3D with this sort of models here, where you have the light source that is shooting the unpolarized light, passing through a first filter. That first filter polarizes light to a specific angle. This hits the surface and then bounces back, and the specular reflection is still polarized. And then I've represented this diffuse kind of going out in all directions, that is newly emitted unpolarized light. When the specular reflection hits that second filter, it is getting blocked out completely, and all that is left that you see is those diffuse components. So this right example is trying to illustrate that depending on the rotation or the orientation of the two filters, we are either allowing the specular component to go through, or we are perpendicular and therefore blocking that specular component. And so you can see here, if they're both horizontal, then the horizontally oriented light is going to go through, and then if they're both vertical, the vertical oriented light is going to go through, and if not, it is going to block the specular reflection. But we do always see this this partially polarized diffuse reflection. And remember, it's partially polarized because like half of the diffuse is going to be gone because it is going through that filter over the lens, where basically you're only seeing the vertically oriented diffuse component or the horizontally oriented diffuse component. So adding both a polarizer to the light source and a polarizer to the camera, we get the two different results depending on the orientation of those polarizers, either a parallel polarized image or a cross polarized image. When the polarizers are parallel, you will see the specular component along with a partially polarized diffuse component. When the polarizers are perpendicular or crossed, the specular component is blocked, and all that it remains is the other half of the diffuse component. So you can see in these two examples that we always see a diffuse component of the item, but depending on how the individual is rotating the polarizer, the specular component seems to just completely disappear, and we get the true diffuse component of this material. The parallel polarized image gives us the specular and the partial diffuse, only the diffuse component of that orientation. The cross-polarized image negates the specular and only shows the other half of the diffuse component. So to isolate the specular component by itself, we take the parallel polarized image, the specular plus partial diffuse, and minus the cross-polarized image, the partial diffuse. When both of the diffuses are canceled out, we are left with the specular component. Here we have an incredibly relaxed man's face and a parallel polarized image here with the spec and the partially polarized diffuse. And then the cross polarized result with only the polarized diffuse. And if you minus those, the diffuse components get canceled out, and all you're left with is the specular component. This cross-polarization photography allows CG artists to collect photogrammetry data of everyday objects, and allows them to recreate these objects in 3D with accurate diffuse and specular maps for physically based rendering. What seems just like theoretical diffuse specular render path separation in CG is actually a lighting phenomenon that can be separated into diffuse and specular components in the real world. And I don't know about you, but I think it's incredible that we get to see the diffuse and specular components of like everyday items just by how we're taking the picture with polarized light sources and polarized cameras. Notice that metallic materials have no real diffuse color to them. They show up as completely black in the cross-polarized result. This harkens back to the previous video where we talked about metals versus dielectric materials, and that metals are entirely surface level specular reflections, which is why they get cancelled out in cross-polarized photography. Occasionally, the diffuse components of parallel polarized and cross-polarized images are slightly different, a brighter or a shift in colors, for example. In this case, when we minus the cross-polarized result from the parallel polarized result, we're left with this leftover color information, or artifacting. That's referring to kind of these sections of the image here where this girl appears to be blue. But as we know from specular reflections should be the color of the light. And the color of the light is not blue, and her skin is not blue, and the specular component of her skin is not blue. So kind of it's an artifact of what's going on. It's probably better represented by this leaf, where basically remember that we're only seeing half of the diffuse component at any given time, depending on how we rotate that second filter. And that is assuming that both of the diffuse components that we're seeing are equal, but they might be slightly different. And when you minus them, you're going to get a little bit of difference, and maybe that is going to show in some extra color. The specular component result can be desaturated to compensate for those kind of color artifacts. But do remember that in dielectric materials, the specular component is the same color as the light source, but metals can actually tint the specular color depending on the type of metal. So you might not want to desaturate all the time if you're taking photographs of metallic items. Light stage cross-polarization. The light stage used in films is capturing evenly lit cross-polarized textures of various facial expressions. So the light stage is filmed in a controlled lighting environment where the only light that is shining is the lights all around the character in this light stage, and all of those lights are polarized. And of course, the camera is also polarized, giving us this cross-polarized result, and this helps separate diffuse and specular, and also aids in the tracking of the features of the face. Because if you think about it, when specular highlights are rolling over the face, it might interfere with some of the tracking markers on the face. So it's better to view only the diffuse component where we can see all the tracking markers perfectly. It'll also help us in gathering these incredible high resolution images for bump and spec maps. So as opposed to previous images that we were looking at where the cross polarization was flash photography from the camera to get a nice flat texture, the light stage is actually allowing us to capture different lighting scenarios from different angles and seeing kind of the different specular that is happening as the light rolls over the face, and just, different lighting scenarios, either front on or top view or from the side or back. And yeah, it's just gathering a lot more of this reference for us. So that is all for this bonus video on the material AOVs about cross-polarized photography. I thought this was an incredibly cool subject when I started learning all about the diffuse and spec components, and that you could actually separate them in real life, and that it wasn't some like theoretical thing that you do on the computer when you just click the separate diffuse and spec button on the renderer. These are actual lighting concepts that exist in the real world. And I think just knowing that can improve your understanding of lighting. So I hope you enjoyed this kind of nerdy walkthrough and maybe learned something. I certainly did when I was making this video. And yeah, I'll see you in the next video. Thanks.